ever lay awake at night wondering how it'll all end? And I mean really end, like the whole universe.
Yeah, the ultimate curtain call.
Right. Well, today we're tackling a big one. The Big Crunch. We're diving headfirst into this mind-blowing idea.
Absolutely. We're going to unpack what it is, the history behind it, the science that makes it tick, and why, despite how captivating it is, it might not actually be the grand finale some once thought.
So instead of the universe endlessly expanding, picture this. It's more like a cosmic boomerang.
Okay, I like where this is going.
Thrown outward by the Big Bang, but then eventually gravity says, hold on a sec, hits reverse, and everything gets pulled back together in one, well, spectacular cosmic implosion.
It's a pretty powerful image. And it's an idea that's really captivated thinkers for centuries, actually. Believe it or not, the seeds of the Big Crunch were actually planted way back in the 1700s.
Get out! Back when telescopes were like basically fancy tubes.
Oh, yeah. Long before the Big Bang was even a twinkle in anyone's eye.
So what, were they just sitting around pondering the universe between cups of tea?
Basically. Imagine yourself under those starry skies, right? And someone poses this question to Sir Isaac Newton himself. If gravity pulls things together and the universe is chock full of stars, wouldn't it all eventually just clump into one giant megastar?
That's a good question. I mean, it makes sense. If you left a box of magnets alone long enough, they wouldn't just float around politely forever, right?
Exactly. And that, my friend, is the crux of what's known as Bentley's paradox. It gets at the heart of gravity's role in the universe's fate. Even today, with all our fancy telescopes and equations, it really makes you stop and think.
Talk about humbling. So
Right.
how do we go from 18th century pondering to the Big Crunch as we know it today?
Well, fast forward to the early 20th century. Einstein, in his early days, was surprisingly into the idea of a static, unchanging universe.
Really? Static.
Yeah, he was. But his own theory of relativity, it suggested otherwise.
So he had to like pull a magic trick to make it all fit.
Something like that. He introduced what he called the cosmological constant, basically a force that would oppose gravity and keep everything from, collapsing in on itself. It was kind of his way of saying, whoa there, universe, not so fast.
A bit of a cosmic tug of war then.
Exactly. But, like any good scientific theory, it needed testing.
And cue the dramatic music.
Enter Edwin Hubble, stage left, with his absolutely groundbreaking observation. The universe wasn't static at all, it was expanding.
Whoa, plot twist. So much for static. But how does an expanding universe lead to a big crunch? I mean, those sound like they'd be like fighting each other.
It's a bit like if you throw a ball up in the air, right?
Okay.
Initially, the force of your throw, it overpowers gravity, so the ball flies up.
Right.
But gravity, it never really goes away.
Right.
It slows the ball down, and eventually, well, what goes up?
Must come down. Okay, that makes sense. But, I mean, is there even enough stuff in the universe, enough gravity to pull off that kind of cosmic U-turn?
Now, that is the billion-dollar question.
Right.
The universe needs to have a certain density of matter for gravity to eventually overpower that expansion.
Okay.
Like a cosmic balancing act, basically.
Got it.
If there's enough, the universe goes up, slows down, and then crunches back in on itself.
Okay, so for a while, this whole idea of a big crunch followed by another big bang, this kind of cosmic cycle, that was a big hit, right?
Oh, absolutely. It's a captivating idea. This endless dance of expansion and contraction. Universe is basically being reborn from the ashes of their predecessors. Even Einstein, after he kind of got over his whole static universe phase, he briefly flirted with the cyclical model.
So instead of one grand finale, we've got an encore performance. Sign me up. But tell me more about these cyclical models. Like, how do they actually work?
Well, probably one of the most intriguing ones is the Big Bounce. And it suggests that the universe, it endlessly cycles through these big bangs and big crunches.
Okay.
Almost like a beating heart.
A cosmic heartbeat. That's kind of beautiful, actually. But it gets even wilder, right? You mentioned something earlier called the, was it the ekpyrotic model? Yeah.
Now imagine, instead of just one universe, there are multiple universes or brains just floating around in this higher dimensional space
Okay.
that we can't even perceive.
Okay.
And every now and then, these brains, they collide. And bam, that's your Big Bang.
Hold on. So it's not a singularity where everything is packed into a single point. It's more like a cosmic fender bender.
That's a fantastic way to put it. And these brain collisions, they create the energy and conditions for a new universe to form. And then instead of a complete collapse, the universe, it bounces back after reaching a certain point,
Yeah.
driven by the energy from this collision.
So it's like a cosmic trampoline park with universes just bouncing off each other for all eternity. Each bounce a new Big Bang. I gotta say, that's a lot more fun to picture than everything just collapsing in on itself. But where does dark energy fit into this whole brain bouncing model? I mean, we've all heard that's kind of a big deal when it comes to the universe expanding.
Oh, absolutely. And the ectorotic model, it tries to explain dark energy as a force that arises from the interaction between these brains, almost like I guess you could say like a cosmic spring that kind of pushes them apart after a collision. And in this model, the dark energy is the engine driving that expansion.
So instead of gravity winning out in the end, dark energy is saying, nope, we're going for round 2, baby.
You got it. It's a wild idea, but it offers some interesting solutions to some pretty big cosmological puzzles that frankly have baffled scientists for decades.
It's certainly making my brain do backflips. But it sounds like the big bounce, that's not the only cyclical model out there. We got options.
Well, we've got options.
Yeah.
Cosmology is full of surprises. You've got, for instance, conformal cyclic cosmology, or CCC,
Catchy.
developed by the one and only Roger Penrose.
Wait, the Roger Penrose? The black hole rock star.
The very same. And his CCC model, it proposes that the universe, it goes through cycles of expansion and contraction, but there's a twist. Each cycle, it completely wipes the slate clean,
Whoa.
erasing basically all information from the previous one.
Whoa, a cosmic reset button. So every cycle is a fresh start.
Exactly. And here's where it gets really interesting. Penrose believes that we might be able to actually find traces of these previous cycles in the cosmic microwave background radiation. You know, that faint afterglow of the Big Bang.
That's like finding a message in a bottle that's been tossed around the universe for billions of years. Talk about cosmic archaeology. But you mentioned another model, something about quantum physics.
Yes. Loop quantum cosmology, or LQC for short.
Okay.
Now, this one suggests that the Big Bang, it wasn't actually the beginning.
Okay.
Instead, the universe goes through, again, cycles of expansion and contraction. But instead of collapsing into this infinitely dense point during the Big Crunch, it bounces back. And this bounces because of effects that are happening at the quantum level, the smallest scales in the universe.
Yeah. So no singularity, just an eternal dance of what? Quantum fluctuations driving the universe's heartbeat?
You got it. It's a very complex model, but it hints at the possibility that the universe might be, get this, self-creating. It's constantly rising from the ashes of its previous cycles thanks to these quantum effects.
Okay, my brain is officially full. These cyclical models, they're incredible. But you know what they say? There's always a but. Right. So what's the but with the Big Crunch?
You're absolutely right. As elegant as the Big Crunch is, recent observations and research suggest it might not actually be the most likely ending for our universe.
Wait, really? After this incredible journey through cosmic trampolines and quantum heartbeats, you're telling me the Big Crunch might be a bust. You're killing me. Don't tell me our cosmic road trip ends with a whimper and not a bang.
I know, right? That's a bit of a bummer. But as captivating as those cyclical models are, the universe, well, it seems to have other plans. Remember those Nobel Prize-winning discoveries about the universe expanding?
Yeah.
Well, get this. Observations of distant supernovae.
Supernovae.
Yeah, those exploding stars acting like,
Cosmic lighthouses.
exactly. They tell a very different story.
Okay.
They show that the universe's expansion, it isn't slowing down at all. It's actually accelerating.
Whoa! It's like that ball we tossed in the air suddenly decided to turn into a rocket ship.
Yeah, it's like the universe hit the gas pedal.
Okay. So much for gravity making a comeback. But what's causing this cosmic acceleration, let me guess, dark energy.
You got it.
So it's not just some theoretical quirk to make the equations work. It's a real player on the cosmic field.
As real as it gets. And this is where the Big Crunch theory, it hits a pretty big snag.
Okay.
If the universe is expanding and at an ever-increasing rate, gravity's just not going to cut it.
Right, like trying to win a tug-of-war against a runaway train. No matter how hard you pull, you're not going to stop it. So instead of a big crunch, are we headed for a big freeze? Everything just spreads out, gets colder, gets darker.
Mhm. It's definitely a strong contender for the universe's ultimate fate. Yeah.
But there's always a but.
Always a but. Remember Einstein's biggest blunder? The cosmological constant?
Yes. God, I forget. Wait, are you saying that this dismissed, kind of forgotten concept might actually hold the key to the universe's fate?
You never know with the cosmos. Well, the cosmological constant wasn't what Einstein initially thought. the idea of it, this notion of a constant energy density that's filling all of space, it's made a surprising comeback.
Yeah.
And it's intimately connected to this whole dark energy mystery.
Wait, so you're saying that dark energy, it might not be so constant after all, that it could, change over time?
Exactly. Some physicists believe that that's a real possibility.
Okay.
Imagine, instead of just pushing the gas pedal, dark energy could be playing with the brakes or even throwing the car into reverse at some point.
Okay, now you're just messing with me. So we've gone from big crunch to big freeze, and now, potentially, back to a big crunch. More twists and turns than a cosmic pretzel.
It's a wild ride.
Yeah.
But here's the thing. Even if the big crunch, even if it isn't the ultimate end game, the ideas behind it, they've totally revolutionized how we understand the cosmos. We've gone from thinking of the universe as this static and unchanging thing to seeing it as this dynamic, evolving entity shaped by forces that, frankly, we're only just beginning to understand.
You know, it really puts things in perspective, doesn't it? The universe, it's far stranger and grander and more awe-inspiring than we could have ever imagined.
Absolutely. And that's the beauty of it all. We're just scratching the surface of understanding the cosmos and our place in it. Who knows what mind-blowing discoveries await us in the future?
That's a great thought to leave us on. So, to our listeners, keep looking up at the stars, keep asking those big questions, and never, ever lose that sense of wonder. This cosmic journey is far, far from over. Thanks for joining us on this incredible deep dive.
Until next time.